remember this game correctly, this is kind of a pun. Oh, it's on Bethesda's? This used to be a online Flash game. So, this is, you can see I've already done some of it. So what this is you're given a certain RTFM. I love it. So they'll go, yeah, so this is my first D. So they'll go easy, but don't expect some special treatment when you proceed further. I have to complete certain tasks. Okay, as any other engineer, and especially as an engineer training, you have to complete certain tasks. The good thing is, however, that even when designing a complicated device, there's still the option to divide design tasks among more people to achieve higher efficiency. You're lucky you will be, for now, starting with the easy ones and slowly work your way up to the more complicated problems ever faced in computing industry. Engineering is fun, that is why you have chosen it, is it not? Yeah, it's a circuit. So what is a circuit? Yeah, it's a circuit. It may sound fancy, but it's nothing too complicated. There are some wires, voltage changes, current flows, not a big deal. Actually, yes, it is a big deal for electrical engineers. But that's not what's going to bother you. Because the only thing you are going to be focused on are digits. Or digital. Digital signals are simpler than any other analog signals since they are only two possible kinds of information. High voltage or low voltage. Better known as ones and zeros or true and false. You should know that it may not always be true that a high signal represents one. Signal is signal. It sometimes carries information. It's something that carries information. The specific interpretation depends on how it is used. It may turn your car's lights on or detonate a nuke. The meaning is up to what interprets the signal. Tip: true and false signals notation come in handy when playing with combination logic and logic operations. Individual operations can be interpreted using their respective names. Example, an output of an AND gate is true when the first and second input are true. Every circuit consists of a component and wires. Wires can be diverted into more branches using nodes. So a signal coming from one source can be mediated to multiple targets. No, it is not recommended that you use nodes to connect more branches with incoming signals instead of outcoming, which should be the behavior of such connections. Many may argue that it's similar to that of an OR gate, but why not, for the sake of clarity, put an OR gate there then? Also, this way, unattended circular connections can be created. And those worse than the most terrifying horror movie you've ever seen. Breaking the fourth wall, components can be picked up from the component window, dragged onto the game. Depending on what game mode is currently running, you may or may not be allowed to use more components or more components of any kind. Yes, some levels can be complicated and use a lot of simpler components, but this is what engineers want to avoid in real life. Too many components, higher energy expenditure, too much heat, even higher energy expenditure, performance drop, and it goes like this until, if lucky, a certain unpleasant equilibrium, if not lucky, circuit damage. The standard circuit design flow for you as an engineer consists of a few steps. Review the input and output list first. This will give you a minimum insight and help you plan your design table to avoid moving circuits parts due to insufficient space. Define the core functionality. It is going to be addition, data processing, memory mapping. Whatever it is, you need to find out first by analyzing the task given in the Tasks and Hints window on your left. Notice any required signal conversion. Oftentimes, device inputs do not match inputs of your core components. They're either their negation or come in slightly different widths and clocks. Although the last step may seem too obvious, clear wire connections are half of the success. You almost never get it right the first try, and debugging a mess of wires is terrible. A terrible experience everyone had to go through. I know that you'll ignore number 4, so why am I still mentioning it? Just to be ready for the told you moment. When your circuit gets into trouble and you aren't able to simulate it successfully, check the I/O window, see what's going wrong. Check your circuit the way you can see the state of individual wires, find the source of the problem. Green wires means high, red wires means low. Check for circular connections. They're hard to debug and it requires a lot of effort, but they're the only way. Well, not the only. The other one is to start all over again. After you've made yourself confident that there's nothing wrong with the circuit, join the forums and explain your problem. Sometimes our flaws are so obvious we are not able to see them. Of this profession is learning. The learning curve of this profession is steeper than Trango Towers. Be sure to read our tutorial tips wiki if founded, and of course our forums. Discussion is one of the best means of learning, and public face palms give that weird kind of satisfaction. Now let's get to work. When ready to start with the tasks and hints on your left, follow your standard design flow procedure. With a bit of effort, you'll get the hang of it pretty quickly. You need to design a device that will perform a logical multiplication on inputs A and B and forward it to the output O. Okay. So first off, I need my inputs A and B. I need my outputs, and I need to do a multiplication on it. And I think, yeah, the AND gate is the only one that I can pick right now, because I'm in the tutorial. Wire placement, I need to go from there to Start the simulation. Next step. And this game, it's just kind of... It's a different kind of puzzle solving. Combinational logic. It has not been said before, but what we've been dealing with in the previous level was an instance of combinational logic. Logic, in the EE meaning, electrical engineering meaning, of the word, can be either combinational, sequential, combinational or sequential. Combinational logic is sometimes also referred to as time-independent logic, and it is always a function of present outputs, nothing else. Example: 1. AND gate takes 2 inputs, and the result can be determined only by knowing those 2 inputs. The same gate could have been used just milliseconds ago to decode whether or not to put sugar in your coffee. There might be aliens in your attic, and World War III might be raging on. AND gates couldn't care less. It would always give us the same output for the same present inputs. The other kind, the sequential logic, is quite different. It is time dependent, and circuits of that type are influenced by previous operations. We won't go into further detail. All you need to understand here is this example. Imagine a coffee machine with an internal counter that stores the information about how many coffees can be made before its precious resources need to be replenished. The counter shall have one output going to a red light saying not enough milk when necessary. Now, most of the time, maybe 40 or 50 times, it won't light up because there's enough milk in the machine. But when that certain counter is reached and the make coffee button is pressed, the coffee will suddenly yell not enough milk and put you into an instant depression caused by coffee deprivation. The output of the machine depends on previous inputs, how much milk had been added before, how many times you had the button to make coffee been pressed. Now I want coffee. What to do with that? Circuits. Combination logic is vital in every type of digital device. It is the simplest form of processing incoming data. When deciding this kind of circuit, you will always be given rules that should keep true for the behavior of the device. Behavior equals response to a sequence of inputs for a device. You are now expected to be astonished by the magic of turning water into ones into zeros and vice versa. You are going to be creating devices that will work, they will produce outputs with specific meanings, and they will eventually make your life easier. Learning to design combinational logic circuits is the very first step to our ultimate goal, designing CPUs. There is not a single CPU that would not use this cornerstone of digital engineering. And as the time will go on, you will notice every new component is just a perked encapsulation and combination of the previous. A CPU is truly nothing more than a huge tangle of interconnected gates. It's time to practice. Try to complete the task given in the task and hints window. Alright. You'll be creating a nuclear bomb detonator. The military has given us some guidelines, so we can't screw up that easily. Inputs, detonate, control sequence passed, detonate and haste. Output, detonate enable, detonated normally. Okay. Okay, output detonator enabled, so okay, so I need an AND gate here. So let's see, when detonate and control sequence. Okay, so when detonate and control sequence are 1, or so that's one input. Okay, why is it not letting me? Or detonate and detonate in haste. So I need the detonate in haste input over here. I need another AND gate. Need my wires. Okay. And detonate normally. Detonated normally will be lit up if control sequence and detonate. Oh, wait. Oh, you know what? I don't need that. Because I'm already creating that signal right here. Because I've got control sequence passed and detonate going through an AND gate. Okay, I think we are ready. See, I saved us a logic gate. Nice. continue with truth tables. Truth tables. So far, you have been working only with devices that are described using words alone, but words are such gross machinery, so primitive and ambiguous. Frank Herbert. A description of behavior by words is not always the most accurate method to specify how things should work. And that's the work of wordsmiths, by the way, not engineers. To describe what inputs yield what outputs, truth tables have been invented. A truth table is nothing more than a table in which each row represents one possible variation of inputs and outputs associated with it. Truth tables do not have to be complete neither, yet they are a faster form of behavioral description, popular among engineers, and usually give you the grasp of the situation at a glance. You're going to use truth tables today to design a device. Generally, when you want to achieve, or what you want to achieve is to process the signals of each row of the truth table to form an output at the same line. Then you will attempt to draw general conclusions that keep true for a group of cases and simplify your circuit. If you're interested in making your job easier, check out Carnog's map, but those are just an intellectual bonus. And by the way, a few new components are now available. Be sure to get to know them and possibly use them. Alright. So what do we got? You're designing a combinational device operating a switch on a bus door. The switch is there to open the doors when necessary. The doors may be opened in different situations. It is not blocked, and the bus drivers... Can I create a truth table? Okay. It's not blocked, and a passenger requested its opening. There is an emergency situation, and either passenger or a safety device requesting opening. Driver open, passenger open is the same. Safety open is a one when the bus's safety device wants the door open, and door blocked is self-explanatory. Open set to 1 tells the door to open. Information about opening informs the driver that the door was opened without his instructions, either for safety reasons or on passenger request. Aha! Here's the truth table that I wanted. Okay, so I need... Where's my... Where's my output? Input, 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 input. Okay, so this is my output. My outputs. Okay, driver open doesn't need to be part of this output. Which one is that one considered? Okay. Passenger open. Safety open, though, however. We're going to need an OR gate here. Because I need... Okay, so safety open. Yeah, every time safety open or passenger open, right? Ah, see. But, okay, so if the door doesn't open, okay, so I need an AND gate over here. Do I have an inverter? Okay. So I need to think about this here for a minute. So, if safety open or passenger open, but, let's see. Okay, I need my door blocked. So DO, I'm assuming, is door open by driver, or driver open. Okay. Door blocked. I need to invert that. Okay, so either one of those, and that is not sending a signal, then we want to trigger the thingy to tell the, what do you call it? So on all of the safety opens, this is the safe, no, this is the safety open. Just to make this a little cleaner, let's move these around like this. Okay, so that's still the same. But what this allows me to do is I want an OR gate up here. And I want another AND gate here. This is the driver open. That's the AND gate. That's the OR gate. That's an OR gate. Okay. Okay, the first line is the truth table. One zero zero, and we output 1 0. Okay. Next step. We pass. We pass. We pass. Okay, so okay. Stop the simulation. I hooked that wire in the wrong spot. And I need another OR gate. So, if the door's not blocked and either one of these happen, yes, okay. Okay. Safety should always open the door. Now let's try it. Okay. Good. That's good. That's good. It's the one that failed last time. Okay, good. Yeah. So yeah, it's not opening the door now because the door is blocked. 011. So this guy. So the safety open and the door blocked. Okay, I see what I'm got wrong here. Put that there. Let's see if we can try that. Okay. Alright. Just trying to save an AND gate, but I don't think I can. So, yeah. That signal, because I don't care if the driver, and this signal, then that one. Okay. This one took a little bit more to do. Hey, we made it past number 6. Yay! Continue with addition. Signals are cool, but when it comes to computation, what does a signal tell us? The meaning of a signal is unknown until we see its usage. Yet we want to compute. And because of that, we know we will be dealing with numbers. If we could specify an interpretation of a signal that would be aligned with how numbers work, numbers could be used in our circuit, and we would be one step forward. Before giving you a complete introduction into numbers in digital circuits, this 2 laws should suffice. Let high, true or 1, state of a wire be interpreted as a number 1. Let low, false or 0, state of a wire be interpreted as number 0. Let's go back to the past and try to remember how we performed addition of 2 numbers. We humans are capable of it, so why shouldn't the machines, which are one step ahead in evolution? When we perform addition, we do arithmetics. Arithmetics is as Richard Feynman said, nothing more than a vast array of tricks proven to be true, making it possible to count really fast. We were taught tricks to automate addition and subtraction of numbers, but some of those tricks only keep true in decimal base 10 systems. It's time to expand your horizon. Addition in binary requires less effort than the decimal system. It is also convenient by the means of containing just 2 symbols for each digit, 1 and 0. Since we have just a while ago defined how signals can be turned into numbers and other way around, it is time to put it into practice. Signals coming into and out of a circuit, called adder, will now be considered numbers and treated respectively. We shall now analyze how addition works. Let us lay down first 3 rules of addition in binary systems. 0 plus 0 equals 0, 1 plus 0 equals 1, 0 plus 1 equals 1. We know this is true because we have been told so. If we're adding 1s and 0s solely in this manner, we would not have to think more. But when we try to add 1 plus 1, we face the problem of representation. Should we add a new symbol that would represent the results of such an operation? Yes. Okay, let's denote the result of 1 plus 1 by 2. What's 2 plus 1? Shall we again a new symbol for this number? Yes, we could. But when would we stop? When would this stop? We can't create a unique symbol for every number that comes into existence. Instead, we decide to denote the result of 1 plus 1 by 10, where the digit more on the left tells us how many results of 1 plus 1 we have. I won't go into explaining the how binary works now. The topic was already well covered elsewhere. I'm just merely pointing out that 2 more rules or tricks are known to us and shall be used. 1 plus 1 equals 0, carrying 1. Addition can be chained on both result and carry to work with larger numbers. Components that perform addition of 2 binary numbers without respect to previous carries is called a half adder. From the first 4 rules mentioned on the previous page, we are able to construct a complete truth table describing its behavior. The truth table can be found in the tasks and tips window. Note, the number of higher significance, i.e. 1 of the 10, that comes from addition is called carry. You will later learn that the carry that goes into the adder from previous additions is called carry in, while the carry coming out of the current one is called the carry out. Design a single full adder. A full adder adds binary numbers and accounts for values carried in as well as out, and a 1-bit full adder adds 3 1-bit numbers, often written as A, B, and C, in. A and B are the operands, and C in is the bit carried in from the previous a less significant stage. The circuit produces a 2-bit output carry, and sum, typically represented by the signal C out and sum, or S. When result equals 2 times C out plus S. A, the first number into the device, the augended. B, the second number to be added, the addended. Outputs sum and carry, a number with higher significance to be moved forward into the computations. Alright, so I've got input A and input B. I've got my sum out, and I've got my carry out. I don't get any of the fancy adders yet. I don't think. Okay. Okay, so I need an AND gate, and an OR gate. And you thought adders were complicated in computers. So, a simple 1-bit adder can be made by just 2 logic gates. So if A or B come in, it comes out as a 1 on the sum. But if it But if it's A and B coming in, then we get a carry out. And thus we have built a simple adder. Oh, darn it. I guess I need more logic gates. But I don't have any more logic gates that I can pull. Yeah, I literally cannot pull anything else into the screen because it says I can only use 6 resources. So 2 logic gates and got to think about this for a minute here. Okay. Oh, that's what it is. I need a and an exclusive OR. That's what it is. So still 2 logic gates. Forgot about exclusive ORs. Now we get to full addition. Oh, I got a pull-up and I got a half adder now. Ooh, and I get more adders later. Yay! Let's see, just adding 2 values was fun, even when the classmate sitting next to you in the first grade didn't think so. Memory flashback. No, Ivan, you can't copy my homework for like the 7th time this week. 6 is enough. Ivan, 6 is enough! The developers of this game were kind of comical. An interesting problem arises when you decide to chain up multiple additions of digits with increasingly significance to add wider, bitwise speaking numbers like 11 in base 10. Base 10 should always be implicitly assumed, if not explicitly stated otherwise. Or, if you do it in binary, it's 1011. Our half adder we designed earlier was capable of producing 2 outputs, a sum and a carry, for 2 inputs, A and B. Have you noticed that despite running out of input combinations, 4, we still didn't use all the possible outputs? You could not have seen sum and carry in the table. That's the empty space we are now going to fill in. Our design goal is to have a component that accepts 3 inputs, A, B, and carry in, instead of just 2, and yields 2 outputs, sum and carry out. Let's examine what exactly are we standing against. You need to perform a binary addition of 3 signals or values, A, B, and carry in, while yielding 2 outputs, sum and carry out. Try to fill in a truth table with 5 columns on your own. Oh, I guess they do it. Here. The truth table that compiles the logic to full addition can be found below. Okay, yeah. I guess we should have... From now on, you're on your own. You now may be wondering what exactly the chaining we mentioned all around this place is. Well, addition of bitwisely wider numbers can be subdivided into separate additions for pairs of digits with same significance. Then, a general rule applies that every carry out line of every adder is a carry in for the following one. An illustration can be found on the following page. An example for 2 4-bit numbers follows. Okay, yeah, so you have bit 1 bit 1 is all the A's, bit 2 is, I guess it'd be a nibble, is all the B's, and the carryover carries out. Okay. Design a single full adder. Full adder adds binary numbers. The circuit 2-bit output, carry and sum, typically represented by carry out sum, where the result is that mathematical equation. A is the first number in the device, B is that, and then we got the carry in, and then we got the sum out and the carry out. Okay, good. They did include the truth table. I was hoping they did. So for the half adder, we know we need an XOR and an AND. We're going to need another XOR. And another AND. Wait. Okay. So, wait. So if the carry or this mess is 1, we output the sum. So if either one of these or that, we output the 1. But if both of these are AND, if both of these are 1, then we need to output a carry out 1. So I might not need that one. So, but if the carry out or one of these, okay, so but if the carry out and one of these okay, so if the carry in and one of those, so I do need that AND gate. So what we got, if the carry out, or if the carry in and one and these, well, if both of those, yeah, so, okay. So if both of the, okay. So, so if one of those, but not both of those, are an out, then we get the sum out. But at the same time, if we've got both of these, then that outputs this. And if both of those output, then yeah. I think we got it here. No inputs, no outputs. We get the carry in, we get a sum out. We get input B in, we get a sum out. Okay, why did that not work? Oh, because this needs to be an OR gate. See, oh, no, I do need... Why do I have no more XORs? Or no, I need an AND gate as well. Yeah, I need the AND gate as well because... Okay, let's retry that. Okay. Okay, what's going wrong here? It's because I tried to save a freaking thing and... It's because I tried to save a freaking circuit. I tried to save that logic, that one logic gate, and since this one was pulling it down, this AND gate couldn't pull it up. Continue with numbers. 2 bits equals 4 states. 3 bits equals 8 states. Signals are cool. There's no lie in that. However, the whole point of computation is that we are working with numbers. As we pointed out before, we need to somehow turn numbers into signals. Remember when we first said that the meaning of the signal is up to how we interpret it? It hasn't been stated, but in the previous levels we already assumed that every signal line, wire, could represent a different digit in a binary number. And since there are two major prevalent wire states, high or true corresponding to 1, low or false corresponding to 0, it sounds feasible to do so. Dealing with numbers in this manner is, however, just a convention. It was the simplest and most natural one available at the time, so it was picked and is nowadays widely applied. If we have a natural number, say 8, we can turn it into a binary form of 1000 base 2, or 1000 base 2, and assign each of the wires A0 to A3 as a digit of this number, and A0 having the least significant. In engineering, counting starts from 0. But what numbers can we actually work with if we have only 4 wires? And what if we have n wires? Going back to the previous example, 1000 base 2 in the terms of its bit width, how many digits does the number have in binary? 4. Okay, that's not a big number. We could design a microprocessor that would work with 4-digit numbers, and unless we tried to work with a number larger than 15, 1111 in base 2, nothing would go wrong. But what about 17, 10001 in base 2? That one needs 5 digits to be represented, as well as other numbers up to 31. It may sound like a big deal, but it may not sound like a big deal, but it is. We are to design something to do computations, and yet we don't frickin' know how many wires and how many components, example, full adders, are needed. The more components, the more expensive our machine gets. And if nothing else, money is important. This is how we come around with the term bit width. It is the width of the bus, a set of wires used to carry digit signals on which operations are performed. We don't need to use all the wires available, the full width of the bus, because the rest of the bus can be filled with extended MSB, most significant bits. Having a 4-bit bus of A0 through A1, as on the previous page, we can represent a number between 15 and 0, a total of 16 numbers. Having an 8-bit bus, we can represent any 8-bit wide number as 10101000 in base 2, or 11111000 in base 2, and we don't use all. And if we don't use all the digits, it's okay. We can fill them with zeros. It won't do us any harm. The bit width of a bus, or of a bus width, specifies the number of numbers we can use, or the maximum and minimum range when a certain convention is used. For example, a natural number with a bit width of 8 will certainly never exceed the value of 255. Similarly, a natural number with a bit width of 4 will be somewhere between 15 and 0 inclusive. One final, I can't read that, remarque. When having a number of a specified bit width, the bit with the least significance is called the least significant bit, or LSB. The bit with the highest significance is called the most significant bit, MSB. So in the case of 1010 base 2, MSB is 1 and LSB is 0. Now go complete the task to demonstrate your deep understanding of the topic. Let's see here. You'll be given 2 buses of 4 wires each carrying a 4-bit number. Your task is to add those numbers and place the results on an output bus of 4 wires. You can complete the task on a pre-wire basis or use the freshly unlocked bus adder. A 4-bit wide number, the first operand, B, another 4-bit wide sum, and carry out. Okay, so I will need my in and my in. I will need my out, and I will need my carry out. I will need my, do I need a full, yeah, I need a, no, I guess I can do a half adder because I don't have a carry in bit. I don't know what happened to the music. I was liking it. It can come back if it wants. Okay. This one should go easy because we're literally using one of their blocks. As long as I wired it correctly. Yay! I got a 4-bit NOT gate. Cool. Alright. Complements. It is time to face another interesting problem. Suppose that we have an integer. If it's positive, we do know how to represent it in binary because every positive integer is natural. But what if it's negative? How do we add that additional information about a sign present? I've got an idea. Let's assume that the first bit of every number is its sign. It will be 0 if the number is positive, or 0, and 1 if it's negative. It turns out, however, that this isn't that practical. We would need a decision-making logic that decided whether the numbers should be added or subtracted, even if we were just adding them together. We would need a separate component that would know how to actually perform the subtraction. The solution is that we think about an alternative way of representing negative integers, a way that would not require any change in our addition mechanism, because we like them. A good method for finding solutions is practiced by physicists and mathematicians when something pops out. They always search for the simplest, closest problem they can solve and try to generalize the solution. We don't know how to find the representation of a number that would complement a positive integer arithmetically equals a negative number, but we do know how to find representation of a number that complements positive integers logically by the means of Boolean logic and digital logic. We can perform a logical negation inversion using a NOT gate or an inverter and get such number. An interesting property of the result is that adding the original number with the number negation form the exact opposite of 0. I don't know about you, but this does not seem grammatically correct for half of the things that they're saying. The process of finding a number that logically complements original as well as the number itself is called one's complement and can be performed by NOT gates. Now that we have a means to calculate a number which complements original in a bitwise manner, it is time to find a number that complements original arithmetically. What properties does such number have? If we add such number to the original 1, the result must be 0. If the number is an arith. Negation of 5, the number plus 5 equals 0, for example. On yet another example, we know that 1001 in base 2 plus 0110 in base 2 equals 1111 in base 2, which equals approximately the inverse 0000. If we could only get a 0 on the right hand, then we should be done. There are several procedures that yield 0 as desired. The simplest one is to add the original plus the 1's complement. And then, demonstration. So, 1001 base 2 plus 0110 base 2 plus 0001 base 2 equals 10000. After stripping off the leading 1, we get 0000 in base 2. And how do we achieve stripping off? We simply ignore the carry out of addition. We solve the problem we thought about earlier. Let a be a number. A representation of negative A is acquired by first finding one's complement of A denoted by inverse A, followed by adding 1. Any number obtained in this fashion yields a summation of 0 of the respective bit width, with original and carry out, now called borrow out, which we will learn to interpret later. This, ladies and gentlemen, is called 2's complement. Ugh. This has got a lot of math in it. Okay, tasks. A is a 4-bit input. A will be given. Find number B such that A plus B equals 0 and assign it to the output. Okay. Okay. So I know we gotta do that. Do I need a full adder or... So I might need that guy. Hi.
Hi.
Okay, so this is probably going to fail miserably, but we're going to try. Okay. We'll just always do the carry in as high and see how this works. Okay. 0 plus the inverse of 0 equals 0. Plus a carry out. Okay, so I need some OR gates, I'm assuming. Except I don't have any OR gates available to me. This probably isn't. See, the best way to do this would be if. Hmm. I hear a dog barking. Be right back. I gotta make sure that it's like nobody brought home a dog. Okay. I just noticed that these are where you guys can't see them. See, it won't give me any OR gates, and That's how I would do this. I would do a 4-bit wide OR gate, and if anything, if I tie that high, this would work, but the next step won't. I think I broke it because I don't think it's supposed to do that. See, that's why I need frickin' OR gates. Not the most elegant solution, but is there a way to use one of these adders, maybe? Four-bit half adder. I don't know. See, I don't understand this. See, how can that be incorrect? Oh, I'm misreading this. That's my problem. Sweeney Todd is indeed a great turn. See, I don't get this. Do you want B or do you want A plus B to equal 0? Because if I did A plus B equals 0, and it fucking told me it was wrong in the second step.